everyone. I'm very pleased to introduce to you today our first keynote speaker of the Rocscience International Conference, Dr. Will Bawden. Dr. Bawden received his BSc and his MS in engineering geology in 1970 and 1972, respectively, and his PhD in rock mechanics in 1980. Following brief periods working in the civil and petroleum fields, his career has been focused on hard rock mining geomechanics, with special interest in underground geomechanical mine design. After working for the Noranda Mining Corporation, Dr. Bawden joined academia and is Professor Emeritus in the Lausanne Mineral Engineering Program, Department of Civil Engineering at the University of Toronto. Along with maintaining a personal consulting practice, Dr. Bawden is co-founding partner of Mining Design Technologies, a boutique geotechnical instrumentation manufacturer based in Kingston, Ontario. Dr. Bawden received the Rock Mechanics Award from the Strata Control Committee of the CIM. He is a registered professional engineer in Ontario and BC, a fellow and life member of the Canadian Institute of Mining, Metallurgy and Petroleum, a fellow of the Canadian Academy of Engineering, and an ARMA fellow. Without further ado, I'll give you Dr. Bawden.
Good morning, everyone, and welcome to all delegates from around the world who may be attending this conference. I'm really pleased to be able to speak to you today and give some reflections on my many years of mining rock engineering practice. Although my talk will be very mining centric, I do hope that everyone will find aspects to take away and gain from this. I don't seem to be able to change the slide. Thank you. So, what is a mine? I'm sure that everyone in this conference has their own idea and vision of what a mine is. However, I would suggest that unless you've had some really quite deep involvement in mining, your perception and reality may differ significantly. There are basically two main types of mines. There are underground mines, the figure shown on the left, which are mines where, other than the metallurgical functions, all other mine operations are located below ground surface. The figure on the left illustrates the Hemlo ore body, a very well-known ore body in northwestern Ontario, Canada. That ore body is about 3 kilometers in length, 2 kilometers in depth, up to 40 meters thick, and dips at an inclination of about 70 degrees to the north. The mine on the right is an open pit mine, meaning it is mined in horizontal layers from the surface down, and that particular mine, when complete, will be about 1 kilometer deep and 2 kilometers in diameter. Next slide. So mining is the second of man's earliest endeavors after agriculture. And it is one of the few methods of actually generating new wealth versus moving money around. In its broadest context, mining encompasses the extraction of all naturally occurring mineral substances, including solid, liquid, and gas, from the earth for human usage. Interestingly, most cultural ages are associated with and identified by minerals, the Stone Age, the Bronze Age, Iron Age, etc. And I guess in today's information age, the mineral we would refer to would be silica. The original mining text, titled De Re Metallica and written in Latin, was authored by a gentleman named Georgius Agricola, and was published in 1556. Not too many professions can trace their history back to that. Interestingly, also, it was translated by Herbert Hoover, who was a mining engineer and former president of the United States. So what is mining geomechanics? It's basically the design and development of safe mine operations and mine openings using a combination of applied geology and mechanics. The first focus is always safety. The second focus, however, has to be on operational efficiency, doing things like reducing or eliminating required rehabilitation of mine development openings damaged by mine-induced stress change. The figures on the right show the, I don't know why that keeps doing that. Figure on the right shows the reported rock bursts and rock burst fatalities in Ontario between 1928 and 1990. You'll notice that both the number of rock bursts and numbers of fatalities reduced dramatically over that period. This is all primarily due to technological advancements, largely in the rock engineering area, combined with a higher degree of focus by corporations on mine safety. In Canada, the Ontario mining regulations are the most stringent in the country, and mining regulations are a provincial jurisdiction. And the Ontario regulations are generally used as a template for most other provinces. Mine site workplace injuries and fatalities pose very serious consequences for corporations and their executives. You will all, I'm sure, be aware of the last major tailings dam collapse in Brazil that killed several hundreds of people. The senior executives for those areas of Vale have been charged with very serious criminal offenses and will probably face prison time. Back in the 70s and 80s, mine site injuries and fatalities resulted in no less than 3 provincial inquiries into mine safety in Ontario. Now, provincial inquiries such as these in Canada usually generate a great deal of paper and often not much else, but these actually had very, very positive outcomes. There was a significant increase in R&D funding, both industrial and governmental. That resulted in new and improved ground support elements and practices, improved instrumentation, new empirical design tools, new numerical modeling tools. All of that combined resulted in a significant measured improvement in mine safety. And today, mine safety statistics exceed those for the forestry, agriculture, and construction sectors. So, geomechanical design is fraught with uncertainty. Where does that come from? Well, let's look at basic geology. It comes from spatially limited data, which requires interpretation and interpolation. Geotechnical core logging and mapping has to be used to determine the various geotechnical parameters. And there is uncertainty in all of those. Geotechnical parameterization, the risk there is accumulation of the above two. Modeling presents its own problems. One has to decide on a constitutive law, commonly the generalized Hooke-Brown or Moore-Coulomb. And the key constitutive parameters have to be estimated based on the above mapping, etc. The uncertainty then for that is the cumulative of the first 3. Notably, all geomechanical problems are 3D. Even if the geometry can reasonably be simulated in 2D, the geology never can. So, to my mind, there appears to be often a disconnect between the end users of numerical modeling software and what their models are actually meant to deliver. Firstly, even the most sophisticated models are not reality. They are at best highly simplified approximations of complex physical problems. As most basic, a model needs to do the following: represent the problem geometry as accurately as possible, apply appropriate boundary conditions, use the best estimates of the Farfield stress regime, and apply the most suitable material constitutive laws. Each of the above carries on uncertainty that must be accounted for when interpreting and using modeling outputs. Examples of uncertainty, for example, the Farfield stresses. The data shown here is taken from the underground, the underground research laboratory that was run by Atomic Energy of Canada in the province of Manitoba. This facility was conducting research for the ultimate long-term disposal of nuclear waste in a deep geological repository. It was an underground facility, and once the shaft was sunk, stress measurements were conducted before the shaft was sunk and after. And those are the data shown herein. This facility was located in a massive undisturbed granite batholith and represented one of the most homogeneous and isotropic rock masses one could find. The shaft was intersected by 3 major fracture or fault zones, but there was no conventional jointing as we normally expected, and it was a uniform lithology. The figure on the right, the solid lines on that figure are the extreme and normal lines from Dr. Herget's 1986 database for stress measurements in the Canadian Shield. It's notable that the stress measurements at the URL do not follow those limitations at all. It's also notable how much variance there is on each level for each of the stresses measured. Hence, if this is a much simpler rock mass than any mining operation, and hence the stress field of a mining operation would be expected to be far more complex than what is shown here. So how does one determine what the best Farfield stresses are to apply to the model? This shows the variance and uncertainty in mapping and logging data. This is just 4 of the many parameters. And the variance shown here is typical. The geological strength index has become one of the most commonly used tools in the geotechnical toolbox, and is used specifically to help parameterize geotechnical parameters for numerical modeling. The GSI values can be calculated based on measured Q prime values, or can be estimated visually as is shown here. Irrespective of how one does this, GSI is never a number. It is always a range. It's really quite inappropriate to say this area has a GSI of 70. It's really probably somewhere between 60 and 80, or perhaps even more widely diverse than that. The next problem comes in scaling to field scale rock mass properties. The figure on the left shows a graph for the Hook-Brown, unified Hook-Brown criteria. As Dr. Hook stated yesterday, we can determine the intact constitutive behavior really quite accurately. And it's appropriate to show it as a simple regression line through that data, because that can be done with well-controlled laboratory tests. The rock mass strength, however, is quite a different story, and is usually estimated using the GSI. As noted, though, the GSI is never a number. So what is shown as a line in the left-hand graph is actually not a line. It should be shown as a band from upper to lower bound. But that's only the beginning of the problem. From the mining perspective, we are never really worried about movements of millimeters or a few centimeters. We're worried about tens of centimeters to meters. And all of that occurs in the post-peak. And that is shown on the right-hand figure. Unfortunately, the uncertainty in evaluating post-peak behavior is vastly greater than that in estimating the peak behavior. It can range from fully ductile to fully brittle, but most of the time resides somewhere in that softening zone. And estimating those parameters is up to the individual engineer's judgment. So how do we deal with the inherent uncertainty? First, we need to collect sufficient data. We need to define the statistical distributions for each parameter. We need to make sure that the people doing that actually know what they're doing. We need to evaluate different design techniques for fitness for purpose. We have a whole variety of possible approaches: analytical, empirical, numerical, etc. We have to decide which one is most appropriate for our particular problem. We have to evaluate the potential for model calibration. Would it be qualitative or quantitative? Is the data being collected sufficient and of sufficiently high quality to justify a nonlinear model? Can a calibration effort even be justified? Also, geomechanical mine design is never a one-step process. Mines evolve over time, and my design and risk assessments must evolve with it. So one way to address uncertainty and risk, of course, is through the use of a factor of safety. That's the classic approach. However, a factor of safety must be determined by some person, some engineer. It's a decision some person has to make. Often it's made based on precedent in the literature. For instance, perhaps large slopes normally have a factor of safety of, say, 1.2 or 1.25. However, what does that mean? Why don't we use probabilistic analysis, where we can take into account all the uncertainty? Well, that, of course, that's good if you have adequate data. If you don't have adequate data, you really can't do that. And I suspect that a lot of people are still uncomfortable with dealing with the idea of probability of failure. I have found that using a cumulative probability curve for key parameters is really a very useful approach. And the figure on the right shows a cumulative probability for some parameter, perhaps UCS or GSI, whatever. So you can decide what value you want as a design value. You could, for instance, pick 50%, but that says half of the values will not achieve your design requirement. So you can then reduce that to 30% or 20%. Ideally, you'd reduce it to 0, except that has very large cost consequences. You could use model calibration to try and achieve this, but that process itself is fraught with uncertainty. So the question is, what is the right answer? We can try and use instrumentation to help us with calibration. But first of all, it once again comes down to data quality. The data shown on the left-hand plot is utterly inappropriate for any kind of calibration. The instrument sat there for 400 days with no one taking a reading until suddenly something happened and they decided we should look at that data. It's of no use. The data on the right is applicable for calibration, and the changes in the deformations are directly tied to proximate blasts, so one can attempt to use this for a calibration. But you need a lot of this quality of data if you're going to calibrate a large model. Let me give an example from a very old case study for the Nerita mine, which is a mine operated in northwestern Quebec back in the 1980s. The figure on the right is a longitudinal section through the lower part of the ore body, which is being mined by what is called the transverse open stope mining method. The circles with the numbers is the mine sequence, and where those are shown, those are solid pillars remaining. The blank areas have been mined and filled. And the zone labeled A zone up to surface was fully mined out. The shaft was located to the left of the ore body and about 100 meters off section. This section is actually from a early displacement discontinuity model used as part of the modeling for this analysis back in the 1980s. Straight, simple elastic modeling. The modeling indicated that the pillars would likely fully yield and the stresses would be shed onto the abutments. This made management nervous that perhaps the shaft would be disproportionately affected, and that shaft was to be used for hoisting ore from a satellite ore body that had been found. We instituted an instrumentation program using closure stations, extensometers, and stress cells, all vibrating wire instruments. We set some stress cells and extensometers towards the shaft area and others within the secondary pillars. And we shortly saw that the stress cells towards the shaft the stresses were increasing, whereas in the secondary pillars, they were decreasing. If we look at the extensometer data, the graph to the left shows a shaft pillar extensometer showing very little movement. Graph to the right shows the pillar extensometers showing very large movements, again tied to proximate production blasts. So what does this mean? Increasing stress with very limited deformation suggested that the shaft area was still in the total elastic range. The pillar data, however, with very rapidly dropping stresses and very large and accelerating deformations, suggested we were in the post-peak. The instrumentation results then confirmed the veracity of the original prediction of the simple elastic modeling and allowing the mine to extract the remainder of that ore body. So is this a qualitative calibration or a model validation? I don't really know. From the mining perspective, it worked. The advent of the personal computer and the subsequent explosion in affordable computing power and ever more powerful software have, to no question, brought us great advantages. However, from my perspective, they have also created some new problems. And there are several critical issues that have emerged, at least in the mining sector. There's an increasing reliance on modeling as being the answer. There's a failure of many end users and management to understand the real purpose and power of modeling. At its most basic is to investigate potential failure modes, test sensitivity to variation in input parameters, and assess risk under various assumed conditions. There's also an increasing reluctance of some engineers to go underground and observe actual ground behavior, which is absolutely critical for any kind of model calibration. I note that there is often a fundamental lack of appreciation at almost all levels, but most often most acute with upper management, of the fundamental uncertainties inherent in all geomechanical numerical models, but particularly with complex nonlinear models. The fact that complex nonlinear models do not provide unique solutions, and thus that their even calibrated models results may depart significantly from real behavior, is generally lost on upper management. The recognition that modeling complexity must match the available quality and quantity of data is also often missed. There is really a limited understanding of basic rock engineering principles and applied geomechanics aspects such as empirical design, instrumentation, model calibration, etc., generally due to inadequate training, both at the university level and on the job. And finally, the overconfidence of some senior managers and some practitioners on modeling results, I believe largely driven by the impressive graphics produced by modern software, which they tend to equate to being convincing geomechanics results, and often lack an appreciation for the simple but useful empirical empirical models founded on real-world cases. There's a general lack of appreciation, even often within the rock engineering community, of the limits of model calibration. And this is particularly acute with the use of highly complex nonlinear models. There are significant challenges in achieving any level of confidence in calibrated models. There's a general lack of appreciation of the criticality between different kinds of instrumentation used in the calibration process. The correct use of instrumentation measurements to validate and calibrate numerical and empirical design models is often not well understood. There's a lack of awareness that models do not and cannot provide the answer. That remains the job of the engineering and management team to determine the best answer for the problem at hand. They need to assess all the design analyses available and decide what's most suitable to their problem. Also, management needs to communicate the corporate appetite to risk such that engineers can translate that into required factors of safety or probability of failure. Let me give you an example of what can happen with overconfidence in model results. A novel mining method was proposed for a new mine in province of Quebec. And in this particular mine, opening dimensions were proposed that were well outside of experiential norms. The mining company then engaged a consulting firm to assist with the geomechanical design. Using 3D mine-wide nonlinear numerical modeling, the design engineers concluded that the new excavation span would be stable without backfill. Unfortunately, the design did not work in practice, resulting in significant surface displacements and damage. Consequently, the mining company suffered substantial economic and reputational damage. A forensic review concluded that the original geological model was inadequate and that significant structural details were missing or misinterpreted and had contributed directly to the failure. It further showed that use of the simple empirical stability graph method would have revealed this. It should have raised red flags and initiated a more thorough investigation before implementation of the design. These investigations would likely have uncovered the deficiencies in the geological model and forced a more critical evaluation of the differences between the numerical modeling and empirical predictions. The case illustrates that not only geomechanical numerical models bring inherent uncertainty and risk to design, as in this case, it was the basic geological model. Once the revised geological model was introduced, the numerical and empirical results aligned. There are also limitations with empirical design charts. Early in my career, Dr. Hook cautioned me not to undervalue empirical methods, and the best advice I was ever given. Although these models are far less sophisticated than their numerical counterparts, their basic simplicity and grounding in real-world data definitely offer advantages. Within certain limitations, empirical and numerical results should be expected to broadly agree. For instance, whether a stope would be predicted to be stable or unstable. However, we must exercise healthy skepticism with empirical models if we use them outside of the primary database limits as shown by the red lines in the figure on the right. As soon as you step outside of those bounds, you're really on your own. The geomechanical design is a process. And I think Dr. Stacy's wheel of design is a beautiful illustration of that process. In my opinion, geomechanical design should follow Einstein's maxim that problems should be made as simple as possible, but no simpler. Design teams should logically begin with simple models. For example, linear, elastic, or empirical models to capture basic expected behavior. Then move on to more complex analyses only when they can justify that with more and better data and improved understanding. Some final words of caution. Even with significant effort from knowledgeable and well-intentioned users, a non or weakly calibrated 3D nonlinear model can be dangerous. Why would I say that? Basically because end users, engineers, operators, and management may blindly believe it. Even supposedly well-calibrated models are not totally free from risk, and training in model calibration techniques and limitations remain difficult to access. However, operations must realize they have a duty of care to ensure that responsible personnel receive appropriate and up-to-date training in all critical systems, and surely geomechanical design has to list near the top of such systems. Thank you very much for your attention, and I would be happy to address any questions.
Thank you, Dr. Bawden. I'm going to go online and read some questions to you that have come in. Thanks for that presentation. The first question is, will you expound on the difference between qualitative and quantitative calibration?
Sure, I do so in the written paper. For instance, a qualitative calibration, we for a long time used microseismic data at the mine microseismic clustering as indicative of the moving yield front of an advancing mining sector. So you can tell whether the ground has yielded or not, because post-yield it will go aseismic, and you would likely see additional deformations and fracturing there, which can be determined from drilling and instrumentation. That would be a qualitative calibration, because there's no hard numbers involved. If you want a quantitative calibration, you need to get into things like extensometers, stress measurements. You can still use microseismics. You probably have to go to a more complicated seismic analysis, where you invert the seismic data and compare that directly to specific geotechnical parameters. And that becomes quite difficult to do, particularly in the scope of a large mining operation, where simple economics can limit the amount of specific instrumentation that's feasible to install in the mine.
Thank you. It's more of a statement, but maybe you can comment on it. A common side effect of super easy to use software, spoiled users. Sometimes it's really worthwhile to at least do the calculations by hand once to know what the theory really is about, so you know the software. Can you comment on that?
Yeah, I would tend to agree with that. I think that's the whole issue of starting with a simple model. In fact, start with analytical, then go to linear elastic, and gradually increase the complexity as you gain more comfort and as you come to understand what your data limitations are. So I totally agree with that.
Thank you. I've got a long-winded one in here. I hope there's a question in there. You mentioned lack of appreciation at all levels related to the faster development of computational tools. So for the new generation of geotech and geomechanics who are exposed to multiple ways to the technology, which process do you consider is the best way to address this? Back to basics, understand the empirical models prior, be ground control, core logging, install and process manual instrumentation. What is your advice on this?
Okay, I think all young engineers need to get out in the field. They need to get several years of good industrial practice so that they really get a good sense of the difference between the reality of the field situation and what the model shows and what goes into that model. They need to have actually logged the core geotechnically to understand the difficulty in assessing parameters like JN and JR and JA. And they need to be able to run some simple models and go underground and see whether the model predictions make sense. Because if they don't, it's not the fault of the model, it's probably the fault of the input. Or it could be the fault of the model, perhaps they're using the wrong model. But I think, and Dr. Hook talked about this yesterday, people entering the rock engineering field who think they want to make this a career, which I strongly endorse. It's been a good career for me. But you do need to go out and, as Dr. Hook quite appropriately said, get your hands dirty. And I have seen a certain reluctance to do that. It's more comfortable to stay in the office and run the models. But you can never know how good or bad that model is unless you get underground and observe what the ground is telling you. And always remember that the miners who are at the face, they are a great resource. They know far more than we give them credit for. They're there every day. They see what's going on. If you will take the time to talk to them and ask them, you'd be amazed at the wealth of data they can provide.
Thank you. That's quite interesting and quite true. How can senior engineers help young engineers to model correctly? How close do you think they have to work together?
Well, I think they probably need to work together quite closely, but what the senior engineers can really do to help, I think, is to make sure that they arrange for the junior people to get appropriate training on the models. These models are not simple to use. I mean, the companies like Rocscience have made them vastly simpler than they ever were. However, it's it's getting the right boundary conditions. Should you assign the Farfield stresses as stresses, or should you use a deformation approach and let the model determine the stresses? There are many subtle things in these models, and the more complex the model, the more subtle these things become. So we need to make sure that our people are appropriately trained with the use of these tools.
Thank you for that.
One other comment, Joe,
Sure.
is that the senior engineers, though, are really critical in helping guide, in using their experience to help guide the junior engineers in their progress.
Yep. I got another one here. What are some of the empirical models you use in your practice?
Okay, I use them all. I use the stability graph, of course. I use the pillar stability chart. I use Barton's ground support charts. I use Potvin and Head Giorgio's ground support charts. I use empirical charts about mining under fill. I use all of those, and I may have left something out somewhere, but
yeah, that's a good start for all your problems, actually. Will you explain the different post-peak strength models and how they classify on the Hook-Brown chart?
they don't. They don't. The Hook-Brown chart doesn't address post-peak. It can't.
Okay, that one was simple.
Well, yeah, that's a huge misconception. If you think that Hook-Brown somehow addresses post-peak, it does not. You have to fake that. You have to modify the MB values and the S values. And the trick is that there is no theoretically correct approach to do that.
Mm. You mentioned that numerical modeling is a process. How do you generally use modeling in your designs?
Well, again, I would start with the simplest model, simple linear elastic, and test that against what I see in the ground, and then try to advance to nonlinear, but keeping it as simple. I use Einstein's maxim: make the problem as simple as possible, but no simpler. So depending on the complexity of the rock mass, the complexity of the mining situation, then I adjust the modeling to try and get the optimum result. But the optimum result may not be by applying the most complex model in the world to the problem. Sometimes the best results are achieved using a much simpler model because your data doesn't justify the additional complexity. I don't know if that's an adequate answer, but it's the best I can do.
Yeah, thanks. Yeah. This is an interesting one, and you should know something about this because you've done work quite at some depth and temperature. Any comment on mining in hot temperature? Do we use standard empirical models, or do you know any influence of hot temperature on rock or any empirical models? Can we still use GSI in these conditions?
To the best of my knowledge, yes, you can. Hot rock is definitely an issue, but it's more of a health and safety issue I believe, than a rock mechanics issue. I mean, at certain temperatures, the rock will spoil, but if it's that hot, usually we can't have people there anyway. So normally the ventilation has cooled the immediate rock down to some reasonable level, although it may still be pretty hot if you have to work down there. but I am not aware of any detrimental issue with rock temperature versus the GSI or any of these tools. Not in my experience.
Right, thanks. Generally speaking, which would you recommend? A complex, more theoretically accurate model with higher uncertainty of input values, or a simpler, less theoretical accurate model with high certainty of input values? So
that's a tough question.
Trade-off.
That's a very tough question, but it's a very good question. I think at that stage, I would want to test the two and use field observations to guide me as to which one I should proceed with. That would presume that you have the resources to do all of that.
Correct, yeah. This one is interesting, and I don't think the answer is in any book either. What kind of data would the miners actually provide from their experience at the face?
They generally can tell you if the rock starts to spall, or if it has been spalling, what kind of movements they have seen, if any. Are they seeing? Often, I note that that the key thing is going underground. If I go underground, the first thing I look at, especially in a Canadian hard rock mine in the Shield, where we have high horizontal stresses, the first place I look are in the shoulders, in the haunches, and I'm looking for crushing in the shoulders. Well, the miners will have seen that, and hopefully they would come up and tell you. And also, most mines have a system where the miners or anybody can put in a notice to management or to the ground control group of anything they have noted underground. It's always wise to follow up immediately on those and go talk to the miner himself. Don't let it go by. These are often really important observations, but it's these basic observations underground that are key. And the miners have a wealth of information. They know how the ground support is working. Also, a key thing you'll see if you go underground, and ideally we want the ground support, the rock bolts, to be installed perpendicular to the wall or back or face. And sometimes you go underground and gee, it's really odd, that the bolts are all angled. And you think, well, do we have really poor operators or what? Talk to the operator and they say, well, with the equipment they've given me, I can't get the hole in straight because the boom doesn't fit in the opening. And you go, why in hell did management do that? So it's little things like this, but they're really important because the bolts at an angle don't work near as well as bolts perpendicular.
Thanks. Another one, do you believe we should always treat the numerical approach with a degree of uncertainty, even if it is calibrated well and was compatible with the experimental data before?
I would still assume a certain amount of uncertainty, yes, but depends how you define it's well calibrated and in agreement with the experimental or whatever data. The key thing is it in agreement with the observations underground? Is usually far more key than, I'm not sure what experimental data the person is referring to, but the more highly calibrated the model, the better, but just don't let your guard down.
Right. Along the same lines, in your experience, what is the importance of calibrating damage and the numerical model result? Oh,
very, very, very much. I mean, that's a key. Damage mapping is an absolutely key tool in the calibration process. And it's great because if you do mine-wide damage mapping, you can plot that on a 3D mine rendering that we all use now. And you can overlay that with your numerical results. And you should find some interesting correlations that should be very helpful in making forward predictions on how things are going to behave. We've done that many, many times, and it's a really powerful tool. It's a qualitative calibration, really. So although sometimes if you get the depth of failure in the backs and things, that can be related to the actual numerical results and can get you closer to a quantitative calibration. But don't think that qualitative calibrations are bad or poor. They're great. If that's the best you've got, that's great. You know, it's way better than no calibration.
Right. This is an interesting one, a little bit less technical and more political, I guess. Can you comment on the value of review boards as an approach to help increase the understanding of mine management on reliability of modeling predictions?
Okay, well, I have direct experience from being on a number of such boards, and I'm still on a couple. And fortunately, I believe that the ones I've been on have been very helpful to management. In fact, at the one that I've been on now for a number of years, I would say it's been absolutely critical to the mine's survival. So I think as long as you get the right people and the right kinds of people on those review boards, they can be very, very beneficial.
Okay, and I'm looking at the time. I think this will be the last question to give our moderator a little bit of time to close the session. How can we fill in the gap between empirical and numerical approaches for design of support systems? In your experience, how effective are the numerical codes in design of support when we are dealing with fracturing, massive rock mass, and its post-peak behavior, whether in a non-violent or violent manner?
That's a complex question. I find that a lot of the models where we directly model the bolt elements, that gets very, very difficult, in my opinion, for models to generate the right kind of behavior that we actually see in the ground. It's pretty difficult. I'm not to say that you shouldn't attempt it, but I think you probably need to go to the empirical design and put some heavy reliance on that, because that's based on hard, real field data. The models will undoubtedly continue to get better in terms of representing ground support, but in my opinion, we have a long way to go yet on that. That's one of the weaknesses in all models. And trying to model every bolt in the mine is just not going to happen.
I'll throw my own spin on that one. How do you see smart cables helping out in that regard?
Well, smart cables provide actual data on what the cable bolt's doing, and you can calibrate your model to that, in which case you should get much greater confidence in that. Cable bolts are the one support that you can model rather effectively with potentially. And with smart cables, you at least have the chance to test your model and improve it. So I think they could be very, very helpful. That's very self-serving of me, but what can I say?
Well, we want to thank Dr. Bawden for his presentation. All the other questions that are online, we'll capture those, and Reginald and the folks at Rocscience will make a compilation. We'll try to answer those. Reginald, it's all yours now.
Thank you very much, Joe and Will, for this excellent keynote session. I think we've all learned a lot. And so we will take a short break, but that break is also to help us get into the parallel sessions. So if you haven't already looked at the schedule, I encourage you to look at the schedule, look at topics, presentations you're interested in, and find your way into that room. And I'm sure we'll continue to have an excellent time. But once again, Professor Will Bawden, thank you for your insights, and we wish you very well. And we look forward to you teaching more around the world in the universities and helping us become more practical at what we do. Thank you.
Thank you so much, Will.